Welcome everybody. In today's lesson we talk about the concept of isomorphism or of isomorphic groups. Let's start with a simple example. We take the dihedral group of an equilateral triangle, so the set of all symmetries of this triangle, and associate to each of those symmetries a permutation. We did that many times before. The notation now is this map here from this group to this group is called pi, and an element of the dihedral group gets mapped to pi sub g, which means exactly the permutation that is induced by this symmetry. For example, this here is the triangle. R is our rotation by 120 degrees around the center here, counterclockwise. So pi sub r is the following permutation. Vertex 1 gets mapped to 2, 2 goes to 3, and 3 goes to 1. Or in cycle notation, this is a 3 cycle 1, 2, 3, which is clearly an element of S3. And in this way, I get a map from the dihedral group to the symmetric group on 3 elements. Now, this is not just a map, it is also a homomorphism. Why? Okay, for a homomorphism, we need to check that this is true for all elements of the dihedral group. This is harder to write down than to actually understand. I think an example helps best. Let's take R, our rotation, and S, the reflection about this symmetry axis here. Then what is pi of R composed with S? It is a permutation. So let's apply it to, say, vertex 1. So by definition, this is the permutation induced by this composition. So we imagine that first we apply S, so nothing happens, because 1 is invariant under S, and then we apply R, so 1 gets rotated to 2. So the result of this here is 1 goes to 2. Now what is this composition here? We do exactly the same thing. We ask ourselves, well, what does S do to the vertex 1? And then what happens if we apply R to this result in the permutation picture? So again, pi S of 1 simply is 1, and pi R of 1 is 2. So they agree on vertex 1, and in the same way you see that they agree on all the vertices. And there's nothing behind that, because we do exactly the same. We ask ourselves, what does this composition do? Here first in the symmetry picture, here we first move to the permutation picture and then do the composition, but the result is always the same. I hope this was clear enough. Now this homomorphism is clearly injective. We just have to take a look at its kernel. The kernel consists by definition of all elements here that get mapped to the neutral element here, so the identical permutation that leaves 1 on 1, 2 on 2, 3 on 3. But clearly the only symmetry that moves no vertex at all is the identical symmetry, which just leaves the triangle as it is. So the kernel is trivial, and since we know that pi is a homomorphism, it means that pi is injective. Or by simply looking at what pi does, it is clear that every symmetry gets mapped to a different permutation, so injectivity is evident. Now the orders of both groups are the same, namely 6, here 2 times 3, here 3 factorials. If we have an injective map from a set into a set that has the same number of elements, then it is automatically also surjective. So all taken together, we know that pi is an isomorphism, a bijective homomorphism. And from now on we denote this by this symbol here, equal sign with such a squiggly line above it. And you read this as D3 is isomorphic to S3. Sometimes you add via pi, via, I'm not sure. So D3 is isomorphic to S3. And now from the standpoint of group theory, they are essentially the same group, because the only difference is how we denote the elements. Here they are symmetries, R squared, S, and so on. Here they are permutations. But there is a one-to-one correspondence because I have a bijective map. And because this map also is a homomorphism, it does not matter if I take the group operation here in this group or if I take it in the other group, because I have this relation here. So no matter where I compose, I end up with the same result. So isomorphic groups are the same, except that their elements might look different. But the group operation is the same. They have the same group table in the finite case, and of course there's a one-to-one correspondence between the elements. So then it's easy to see that if I have any collection of groups, I will call it a set script G here is a set of groups, and then if I define that two groups are in relation or equivalent, if and only if they are isomorphic, then this clearly defines an equivalence relation. Why? Well, of course, G is isomorphic to itself. Just take the identity as an isomorphism, for example. Then if G is isomorphic to H, of course H is isomorphic to G. Just go the other direction with the homomorphism. Actually, we're going to prove a proposition that makes this even clearer, that the inverse automatically is a homomorphism as well. And for the transitivity, if G is isomorphic to H and H is isomorphic to, let's say, J, then you have two isomorphisms. Then simply take their composition and you get an isomorphism from G to H. So we have all the three requirements for an equivalence relation. And now the factor set. This is the object you should study when you try to classify groups. What I mean by that is the following. Here, for example, if you take all the finite groups as the set, then the equivalence class of the dihedral group of the equilateral triangle contains, of course, the dihedral group itself, then also S3, as we have just seen, then, of course, also the matrix form of the dihedral group. We did that in the very beginning, and maybe much more. But this is not really interesting from the standpoint of classification, because there I ask myself, how many groups of order 6 are there? Then you can say, well, those are not really two different groups. So I identify them, meaning mathematically that I put them in the same equivalence class, and simply ask myself, how many equivalence classes of groups are there? Because there's no new information in discovering new groups that are essentially the same, just in different notation or different labeling. But we already know another group of order 6, which would be Z sub 6. And this lies in a different equivalence class, because this is an abelian group, this here is not. And you will show in problem set 14 that there can't be an isomorphism between a commutative and a non-commutative group. All right, so to sum that up, when classifying groups, so when you ask yourself how many different, really different groups of a given order are there, you should not look at the groups themselves, rather at the equivalence classes. Okay, let's take a look at an example. We take any group G and an element G of order n, and C sub n is the cyclic group generated by this element. Then the claim is that this here, no matter what the group looks like, what the element looks like, this is always isomorphic to the integers mod n. So that means if you understand those, you understand every cyclic group of order n. This is what isomorphism is about. So you can really identify this here with Cn whenever it's convenient for you. Okay, let's prove this quickly. First of all, what does it mean to be of order n, or what is the definition of the cyclic group? This here means, by definition, all the integer powers of G. So we start with G to the 0, which by definition is the identity. Then we have G itself, then we have G squared, and so on. Then we have G to the power of n minus 1. And then, because the order of G is n, we end here because G to the n again is E. And some time ago we proved that these powers actually all have to be different. Otherwise the order would not be n but a smaller number. So I have these n different elements. And negative powers bring nothing new, because G inverse is exactly G to the n minus 1, because if you multiply them you end up with g to the n, which is E. So this here is the cyclic group generated by G. And now it's pretty clear what we do. To construct an isomorphism from here to here, we simply take such a power, because all the elements look like that, and we send it to its equivalence class mod n, which I abbreviate by K bar or K overline. Okay, and all that is left to do is to check if phi really is an isomorphism. So first of all, is it homomorphic? So we start with this here. All the elements look like that, powers of G, so two arbitrary elements of this cyclic group can be written like that. Now, by a power rule that we proved a long time ago, this can always be written like that. And now, by definition, this gets mapped to the residue class of K plus L mod n. But by definition of addition in this group here, this is the same as that. And now this is just phi of g to the k plus phi of g to the l. And that proves that phi is indeed a homomorphism. Note that here we write the operation as addition. Here mostly we write it as the multiplication or the dot. Usually we write it as a dot. So phi is a homomorphism. Is it injective? So the kernel by definition are all elements here. Again, they always look like this, g to the power of some integer, such that phi of this element is the neutral element here. But phi of this element is just the residue class, and the neutral element is the residue class of 0. Okay, so this here is phi applied to g to the k. And now the only possibility for this here to become 0 bar is if the exponent already was 0. Why? Because here we have g to the 0, g to the 1, 2, and so on. We stop after n minus 1. And none of these exponents here are congruent to 0 mod n. So the only possibility for an element to lie in the kernel is if it's of the form g to the 0, so the neutral element of Zn, and this shows that the kernel is trivial, so phi is injective. Now clearly both have order n, simply by definition of the order of an element or the order of a cyclic group. So phi is automatically also surjective because it's injective and they have the same number of elements, so it must be surjective. So taken together, phi is an isomorphism, so these groups here are isomorphic. Okay, to conclude this lesson on isomorphisms, we prove an interesting proposition. Proof is elementary, but the result is quite surprising if you think about it. If phi is a homomorphism between groups G and H, then automatically its inverse map is also an isomorphism. Now the iso part is not surprising because, of course, if this is a bijective map, then the inverse also is a bijective map. But this here asserts that it is automatically a homomorphism. And this is not clear. If you know a bit about topology, there are continuous maps between topological spaces that are bijective. So they have an inverse, but the inverse need not be continuous. So in this case, in the group structure, this cannot happen. If I have an isomorphism, in topology it would be a homeomorphism, then the inverse automatically also is. In topology, this is not true. No, sorry, for homeomorphism, this means exactly that the inverse also is continuous, but this is an additional requirement. It's not automatically fulfilled. Okay, let's prove this. So all we need to show is that this here is a homomorphism because bijectiveness is clear. If you did lesson 12, you should understand that. So we take two arbitrary elements here, h and h prime, for example. Then I can find unique elements in G such that h can be written as phi of G and h prime as phi of G prime. The uniqueness part is not important, but there are such elements. So then we take a look at phi inverse applied to these elements here. Then by definition, this is what we get. But now, because phi is a homomorphism, we know that this here in the parentheses can be written as this here. But this, by definition of composition, is nothing but phi inverse composed with phi applied to G dot G prime. But this, of course, is the identity of G applied to G dot G prime. But this simply is G dot G prime. And now we reverse this here. G is simply phi inverse of H. Okay, now for this I need the bijectivity so that I can write this exactly as phi inverse of H, and G prime is phi inverse of H prime. And this is exactly what we wanted to prove. This is the homomorphism property for phi inverse, which proves this very useful proposition. The same in linear algebra. If you have a vector space isomorphism, then the inverse map is automatically also an isomorphism of vector spaces. All right, to conclude, a nice example from analysis. We already convinced ourselves that the exponential function, going from the group of real numbers with addition to the group of positive real numbers with multiplication, is an isomorphism. X gets mapped to e to the x, simply because the power rule for the exponential function holds, because here we start with a plus b. I'm using a and b and not g and g prime, because the prime could be confused with a derivative. This is this, and then by the power law for the exponential function, this is this, but this is exactly the group operation in our codomain. So the exponential function is an isomorphism, that it is bijective, that we take or accept from analysis. Now the interesting part here is it has an inverse function, which of course is the natural logarithm going in the other direction. X gets mapped to ln x. And now this proposition here asserts that this is automatically a homomorphism. What does that mean? It means if I take here the product of two numbers, then this gets mapped to ln, the inverse homomorphism, plus, because our operation here is plus, ln r plus ln s. And we just proved that. So there's no need to prove this logarithm law, because it follows immediately from the fact that x is a homomorphism, an isomorphism, and proposition 17. All right, that's it for lesson 15. Thanks for listening. As always, try to do some of the exercises, and I hope to see you in the solution videos or in next week's lesson. Bye-bye.